Okay, we've just got two more of these intro lectures. This one is going to talk about the difference between analysis and design. Many of you have taken steel design, so you've already had a design course, but some of you haven't. And so this may be your first design course. You've taken analysis courses, but not a design course. And so I want to talk about that. So here we go. Let me share that. And it's kind of weird. I have to take my glasses off to use my iPad, but then when my glasses are off, when I turn the computer back on, I can't see anything on a computer screen. So you see me like looking like this to turn things off on my computer. But anyway, here we go. Let's talk about the principles of design. So let's compare and contrast analysis and design. In analysis, you're given everything, and often in these kinds of classes, there's even given, like you have given required solution. And in analysis, there's only one answer that's correct, only one correct answer, I should say. There's lots of answers, I guess, lots of wrong answers. But there's one correct answer, and often it's in the back of the book if it's an even problem. And if it's an odd problem, you can get the answer on check. It's a direct solution. You can just follow the steps, step 1, step 2, step 3, step 4, etc., and get it done. And it's very, very methodical. You just start and you finish. So in contrast to that, in design, you have to make assumptions. So for example, you want to design a beam. You need to know the moment. Know the moment, you need to know the load. To need to know the load, you have to know the weight of the beam. To know the weight of the beam, you have to know the size of the beam, which you're trying to design, and you don't know. So you're going to have to guess the weight of the beam to start the problem. Okay, there are many possible solutions and many possible correct solutions. It might be a 12 by 24 inch beam with X amount of steel bars in it, or maybe a 14 by 20 inch beam with different amounts of steel, and they'd all have the correct strength. So it's funny, on the homework, everybody gets the same beams, but on exams, people get different beams. And the solution is iterative. I just told you an example where you have to guess the beam weight. You do everything, you design it, and then the beam is actually heavier than you guessed. You got to do it again. Okay. And what I'm going to do is throughout the course, I'll say, hey, if you guess this, you probably won't have to do it twice. And so just from experience, I can help you out there. And finally, design really is creative. You can take different solutions, different paths to the solution. And so it's really different than analysis. I want to talk a little bit about the history of reinforced concrete design. First, there was working stress design, and I have a separate set of slides next on that. This is what my dad was a civil engineer. This is what my dad used. And actually, I'm old enough that when I took this class, it was still transitioning from working stress to strength design. So I had to learn both when I took the class. But now it's all strength design. And this is kind of interesting. Trey Hamilton, who's going to teach pre-stressed concrete, could talk to this. But there was a movement to combine pre-stressed concrete design and reinforced concrete design all into one to a unified design. Trey was, I think he was chair of ACI 318G, which is the pre-stressed concrete arm of the concrete building code that recently got dissolved. I'll ask him what happened. And yeah, maybe reinforced concrete and pre-stressed concrete are parting ways. I'm not sure. We'll find out. Okay, so this is pre-stress, and reinforced concrete all under one roof uh, in the same house. Okay, unified design. And I guess that house would be ACI. There's also PCI, Precast Concrete Institute. Okay, working stress design. So 1900 to the early 1970s, it uses service loads, unfactored loads. You don't increase them. You do your elastic analysis, so you can use 3200 structural analysis one, and you can use mechanics of materials and those sort of things. And then you just make sure the stress is less than allowable. Now, here's a weird thing about concrete. Every other course in the world, that's stress, right? Or maybe this is stress. We have a rule in concrete that Greek symbols cannot be used for things that have units. Yes, this is the rule. So you can't use sigma for stress because stress has units. And so because of that, we use the letter F for stress. Now, why F and not S? I don't know. But F means stress in concrete. So that's kind of a weird thing. Okay? So whenever you see F, it's some sort of stress, like F prime C, or if you took CE materials for me, F prime C average, it's actually required average. Okay. And after you design your member, making sure that the stress is less than an allowable stress, you check the deflections. Okay, strength design is from the mid 1970s to the present. You factor the loads, you increase them to represent the worst case scenario. This is kind of weird, even though it is an ultimate, and I already just told you that you can't use 3200. It's not appropriate. We still use it. We use elastic analysis. So this is structures one. You can do different things for the structural analysis, and we'll talk about that when we get to the design project. So this is probably not correct. Okay, you shouldn't be doing that. But the strength is calculated using nonlinear behavior. And we'll learn all about that when we get to calculating moment strength or shear strength or axial strength. And then the safety equation is the reduced strength, BMN, is greater than the factored ultimate load, MU. And we talked about this previously. And you still need to check deflections, which we'll do in the project, by the way. Okay. Unified design is just one code for pre-stress and reinforced concrete, as I mentioned. Okay, so that is analysis versus design and a brief history of reinforced concrete design. And then I have a separate set of notes just on working stress design. And this is going to be the last time we see it for the course. We will use the working stress principles, though, to calculate deflections.